Hello, everybody. I'm Brian Malow, and we are coming to you live from Lindau, Germany, and the site of the 74th Lindau Nobel Laureate Meeting. It's a chemistry meeting this year. We have 30 Nobel laureates, more than 600 young scientists, and they're coming from more than 80 countries. So there's some of them walking behind us, and one standing with me right now, Simon Nirenberg, who a fellow American.
Yes.
From Indiana, but you're working
in Rhode Island.
In Rhode
Brown
Island.
University. Well,
Brown
this
University.
summer I'm actually working outside Knoxville in Tennessee, but I study in Rhode Island.
Yeah, and working maybe was the incorrect word. So, the whole thing about the Nobel Laureate Meeting is it's really about mentorship, and the young scientists, as we call them, just have to be under the age of 35. But that means there are some early stage scientists that are 34, and there are postdocs, PhD students, grad students, and probably, I don't know the stats, but probably the minority is I've met a few undergraduate students, and Simon's an undergrad. What year are you?
I'm going to be a sophomore this fall, so I'm incredibly privileged to be here this early. This is, well, I'll say later, but it's been a wonderful time.
Step in a little more into the shot for me. And but let's not clip your head off. Yeah, okay, so Nirenberg, as you just told me. So that's fantastic. I can't imagine what it would be like. So you've known since about April that you got accepted?
Yeah.
Tell me, some of our audience might be young scientists that want to apply to the meeting. Why don't you tell me something about that process from the beginning? How you heard about the meeting? Was it brought to your attention? Tell me about that process.
So, yeah, it was originally pretty much just an email that I saw from, it might have been my department chair or my professor. And I could tell that, at least in my mind, that it's like, oh, this is insane. Like, is this even real? Because I hadn't heard of it. And then I went, well, I don't have much yet because I was a freshman, and this was in October of my freshman year. But I was like, there's no harm in applying for these things. So I asked my professor, who I'd started doing some research with. That was really lucky too that I started research so early. But I asked her, would you write me a letter, and I'll write some essays and apply for this. And then, that was pretty much it. But then I didn't expect anything. I was like, this is something that would be awesome. And then I heard back. The way I applied was through the National Academies of Science. So they do a separate review, and then they write back. And so I think I found it in November or something, that they had accepted me. And I was like, this is amazing. I didn't expect that. And then I ended up, when they accepted me, they then said, oh, now you have to apply to the real Lindau meeting. And then I was like, oh, okay. But for that, you need a second letter of recommendation. And so I was kind of terrified at that point, because I was like, oh, I'm so close. But then at the time, because due to a bunch of things, I hadn't taken any chemistry classes yet. And so I had a chemist I was working with, and I'd taken some physics classes. So I was kind of out of desperation, I guess I'll ask a physics professor and hope for the best. But what I realized that it might have actually helped my application, because I was really coming, from a physics background, I guess. I used to want to only do physics, and then I realized how much I loved chemistry. And so now I do quantum chemistry, which is the best of both worlds. But I kind of very skittishly asked my electricity and magnetism professor to write me a letter, and he so kindly did. And I sent that off, and then almost totally forgot about it, and then heard back in March and April that I was accepted, and I was like, oh my gosh, this is insane, this is incredible. And then I applied for all the other things, not expecting any of that either, and ended up getting a talk, which is also insane.
Right.
So I don't want to lead too far ahead, but
no. But step a little this way for me.
Yeah.
Thanks. And we'll jump to that in a second. But of the 600 young scientists, I don't know the numbers, but a few dozen get the opportunity to present their research to an audience of colleagues and some Nobel laureates. So those are the next gen science talks. But you know what? You said something really intriguing because you were only in like a freshman and you said you were working with a chemist. What do you mean?
Yeah, so I had an interesting story because I think I had very deliberately chosen where I wanted to go to college because of a lot of reasons. But one of them was that this person was there, and I had met her when I visited, and I thought that she was so incredible that I wanted to work with her.
Do you want to tell us
And
who it
so,
is?
Yeah, Brenda Rubenstein. She's phenomenal. Like the best mentor I could have ever hoped for. And you know, I definitely. I mean, I thought I had no chance of being able to come here with having done what I did, but certainly, you know, everything was made possible by her, and not just her, you know, giving me the opportunity to do research that was so great, but also like her advice and her pushing me to, you know, believe in myself and do things. So, you know, she's been incredible, and she's one of the most dedicated scientists I think I've ever met, including, you know, obviously many such people on that list are here, but including people here. So,
Yeah.
yeah.
So I know you've only been here a few days and you've had a lot more experience with her, but this meeting is about mentorship and the motto is educate, inspire, connect. And I just wonder if all those nice things you said about the mentorship you got from her, have you gotten a sense of that from this meeting at all, from the laureates, even in the brief time you've been here?
So I think that it's a different type of mentorship because, you know, here it's very general, whereas with her I'm doing a very specific thing, and it's a long-term relationship, and I'm working on a particular project. So I get bits and pieces of general advice, but a lot of it's focused. Whereas here everything is general, and so I think it's been a different type of mentorship. But I think I've grown immensely from what I've learned here, and you know, it's been incredibly good. You know, the advertisement is that, you know, you can come and that they'll just be standing around and they're happy to talk to you, and that's true. I mean, I was even in disbelief, and you know, really, I think you can ask any questions, and at least in my experience, I've not been judged, and I've asked some really silly questions, but you know, you have to be a little courageous to go up, but once you do it to one, and then you realize they're people and they want to just talk to you, that, you know, I've probably had incredible conversations with maybe 10 or 15 already, and hopefully I'll get to more soon. So, yeah, no, I'm learning an insane amount. I would almost compare it to like a maturity, like a science maturity hackathon, where the hackathon is the idea, you know, you put all of yourself into this project for like a day, and you dedicate everything to growing for that project, and you come out of it having learned so much. My qualm with the hackathon is you don't usually sleep. Here I still get sleep. But
Not much.
But it's like a hackathon for that, because I've just felt like so much progress so quickly, and almost too much for me to even think about at once, that I've just been writing things down, and I know it'll, you know, it really will be hugely life-changing. It already has been.
Excellent. And so, did you come into your freshman year with a major? Were you a physics major?
So yeah, I applied chemical physics. That was the other reason. One of the other reasons I chose the college I did was they had a chemical physics degree, because I knew in my heart at the time in particular that I was really more of a physicist than a chemist. I'm no good in the lab, so I went in thinking, well, this chemistry stuff is really awesome, and I'd love to do it, but physics is what I'm definitely going to do. And so I applied chemical physics with you know, it being important to me that the physics was emphasized at the time. The truth is, people here do all kinds of things, and I very quickly learned, even in college, that it doesn't matter. It doesn't matter what the degree is called. You know, it's what you do. So really now I say I do chemistry, I do quantum chemistry, I do physics, whatever. But I think that's a very verbose way of saying probably chemical physics is. I haven't declared
What would you
yet.
say? What is chemical physics exactly? Is there a way? Can
So,
you just? Yeah.
Yeah, I mean, I think that.
And I should step in a little.
Oh, I'm sorry. Do I
Yeah,
keep
that's
drifting?
okay. A little bit.
Sorry. So I think that.
But you're doing great.
Thank you. And I'm used to kind of putting my hand up here. I got to be careful of the mic.
Right.
I think that, physical chemistry, quantum chemistry, computational chemistry, and chemical physics, in practice, they're all pretty much the same thing. But if you ask a theoretical physicist, all of everything is theoretical physics. Not every theoretical physicist
Right.
thinks that. So I think that there are little distinctions. What I feel is notable about chemical physics is that the emphasis is perhaps more on the physics of chemical reactions. So whereas I think physical chemistry is doing chemistry in a physics adjacent way, whereas I think chemical physics is kind of doing physics to chemistry problems. But I think that it's such a minor difference that really, if the degree were just physical chemistry, chemistry and physics, any of that.
Maybe I should ask you then, because what you said echoed something a laureate told me, and what I've maybe heard from more than one laureate here. It's like it's more important about the kind of questions you're asking or interested in. So instead of those terms, what kind of questions are you interested in?
Yeah. Well, I think there's a lot. One of them, I think the one that really drives me is I want to understand how things work. And I think that I originally was drawn to physics for that reason. But what I realized is that so much of the things that I really wanted to learn how they worked is chemistry. And it's both. It's chemistry and physics. That's why I love them both. But I think I love understanding that. I also want to, I guess how can I do fun things while helping people would be nice. And I think doing chemistry, maybe theoretical chemistry is more removed, but doing chemistry is a very it's easier to see things that help people in my lifetime. And that's not a dig at physicists, because I think that's incredibly awesome and it definitely helps people. But I feel that I like that I get to do both of the fields I love and apply it to problems that I can see as helping people. But I guess if I wanted to be more specific than the broad questions, I want to understand how and why chemical reactions occur, why the reactions that we know are how we know. So my research is part of it is basically trying to understand. Well, we have a really good theory for why Diels-Alder reactions occur. It's a famous thing from an intro chemistry classes called the Woodward-Hoffmann rules. It won a Nobel Prize, and it's part of my research. But I think what would be so beautiful to me is instead of going and developing it from the Woodward-Hoffmann perspective, if we just do calculations and we kind of do the physics underlying it and we get the same answers, that's kind of a beautiful secondary way of approaching it. But I think the Woodward-Hoffmann rules, as established by their creators, are also actually one of the most beautiful pieces of physical chemistry. So I like how reactions occur, why reactions occur. Maybe even more specific, this is the last one because I know time is limited, is
Not really. It's an
how-
infinite universe, perhaps.
Yeah.
Well, maybe not
We
quite,
don't know.
but we have time.
Yeah. Is how and why the wave function evolves and ends up how it is in quantum mechanics, I think is a fascinating question. And of course, chemistry is entirely applications of that. So I think that there's a lot of things that are really interesting. I heard it today described in one of the talks I went to as that chemistry is the study of how matter scales, or something along those lines. And maybe that's not exactly what it was. I wrote it down, but I think that that's beautiful. What drew me to physics and chemistry and statistical mechanics in particular, which is not known for being a happy field, but I love it, is that you take these fundamental principles and you apply them in huge bulk and use them to make predictions about massive things that we interact with. So I can do quantum mechanics and then someone can go verify that, and we can see that that's affecting us now at a physical scale. I think that's so incredible. It's like a miracle that our predictions can be so accurate when our simulations can only run 30 atoms. So, yeah.
I like that. And, you mentioned a little while ago about taking a class in. Again, you've only had your freshman year and you're going into your sophomore year, but you already took electricity and magnetism. Is that normal that in your first year as an undergrad to be taking it like?
I think
Is that normal for, I guess, up for a physics major?
I mean, I think it depends on the school. There's a lot of thoughts about it. You know, most people have some introduction to that field in high school. I did too.
Okay. I had
so
a good
I'll say-
physics class in 12th grade.
Yeah. And I had a great physics teacher in high school and chemistry teacher.
Yeah.
I think that I owe a lot of everything to them. But I think at least, I don't speak for every school, but at Brown, the recommended path for a physics major is to take intro Newtonian mechanics. And I did take that. I learned a lot more than I thought. You know, it goes a lot deeper than you'd think it does in high school. And then take introduction to quantum mechanics, which is like, you know, the ultraviolet catastrophe and relativity and the big concepts, so that you know, broad implications. And then your sophomore year, you would take electricity and magnetism first semester, and they do it relativistically at times. So it's really interesting because you talk about how do electric fields warp when a particle travels near the speed of light. We didn't do that in high school.
I've heard the term before, and it's a fascinating term, but what is the ultraviolet catastrophe?
Oh yeah, so my understanding is that it was in the late 1800s, early 1900s, that people were trying to make predictions about how light, I guess, what corresponds to energy, so what wavelength corresponds to energy with light. And so they had established some empirical laws, but the laws seem to imply, if I remember correctly, something about, well, there were a few cases, but I think it's that there were rules about, well, I guess I'll start by saying things emit light due to their temperature. And everything emits light at its, just because it has temperature, because it wiggles around and sometimes it releases photons. And so people knew this, and they'd established empirical rules. But what they seemed to find an issue was that their rules seemed to say, I think that when you get into the ultraviolet region of the spectrum, it was, I always mix it up, but it was either that the object has to have infinite temperature, and we'd seen ultraviolet radiation hit Earth from stars and such, and we assumed they probably didn't have infinite temperature. We'd made it, and we'd get it when we stand outside. And so that was a problem. And then models, I guess, also predicted some sort of energy singularities, infinite energy. And so there were these big issues, and it turned out to be because we were assuming that light can have any wavelength, that it has a continuous wavelength. And so the very famous discovery of Max Planck was that it doesn't, that its energy is quantized, and it can only have these discrete energies. And because of that, when he did his calculations through, he found that the curve did not blow up to infinity. It started to flatten out and go back when you got to the ultraviolet. And so suddenly we had reasonable temperatures for things in the ultraviolet. So that was the catastrophe, and its solution created quantum mechanics. So
Excellent.
I think it's beautiful.
Oh, okay. Very nice. Very good answer. So clearly, you started liking science early on. Did you, by any chance, were you a science fiction fan? Did that have anything?
I was a huge sci-fi
Because for
fan.
me, that was part of my path. Because
Yeah.
in the 70s, I was going, and it was the science fiction you'd call hard SF, which is not that it's hard, but the science matters and science accuracy matters. And so I grew up reading Isaac Asimov and Arthur C. Clarke and this guy Larry Niven, who wrote about neutron stars and micro black holes and relativistic effects. And Asimov and Clarke also wrote nonfiction.
Yeah.
And with personality, and Asimov wrote with humor, and it's like, oh wow, I like their science fiction, and now I'm learning science from them. And so I was a big science geek, junior high and high school. What kind of science fiction have you liked?
I will say, I grew up obsessed with Star Wars.
Yeah.
And that is certainly not hard sci-fi.
Right. A lot of people just say it's fantasy.
Yeah, I mean, I think it is. I think that the things I liked about it are just things I like in general, and not so much related to my love for science. I do think the fact that it was in space and had lasers was pretty fun,
right?
Because I was already interested in science. But I think every kid thinks space and lasers are fun.
Sure.
So I think that I actually was not a fan of Star Trek initially, and it was kind of a silly reason, which is that I started it, And then I saw some episode that referred to like a nuclear apocalypse that had happened at some point, or the nuclear war that happened in the Star Trek universe. And I felt that it was almost the hard sci-fi at that point. It was close enough to reality that it kind of spooked me, and I was like, I'll go back to Star Wars. I like my Jedi. I like my lightsabers and. But now as I've gotten older, I think in middle school and high school, I very much came to appreciate the hard sci-fi. Things like Black Mirror, things like The Martian, which has some inconsistencies, but is well known for being phenomenally accurate.
Yeah, the author of The Martian, whose name escapes me right now, but he has a new book, and I just last night saw a trailer, Project Hail Mary, and I couldn't quite tell what it's about, but it looks interesting.
I feel the same way. I also have not read it. There's a group of students at my work right now who read it together, but they read it so quickly. They read it in like 2 weeks, and I was stressed preparing for this conference, so I was like, I don't have time for this, but I want to read it later. Probably before I see the movie. Actually, maybe after, because oftentimes the book makes the movie seem bad. But,
right.
So I love that. I was really into mythology. I loved books like Percy Jackson and stuff like that. So I think it was a fantasy thing for me. But I like
it's speculative. To me, it's like it's imaginative, it's speculative, even if it's fantasy but science fiction really is, and it's not like predicting the future, but it's often extrapolating and taking ideas and extrapolating. So so I'm a big science fiction fan, and I think that's connected to why it was physics and astronomy that I really liked. So that's fantastic. I love your view of science, and I was this, maybe not as deep as you, but I took calculus in 12th grade, and I had a really good hard physics class, and I enjoyed taking the tests. They were challenging, they were hard, and I liked it.
No, I think that was one of the things that I noticed too, is things that are hard often, like just because they're hard, or I would rephrase that, a lot of times people who don't like studying or learning don't not like learning. They don't like the discomfort of not knowing. And I think that that's something that I have recognized too, and it's scary. But I think that what I learned very quickly was that there's so much joy you can have in going from in seeing something and not knowing it at all, and then you do the work and you think about it a lot and you do your diligence, and at some point it's not usually a serendipitous like click, but at some point you look back and you go, I get it now. Like I've had this, I think my most recent really wonderful example would have been my linear algebra class. Was completely pure math based. Like we started by proving that 1 + 1 is 2. Actually, we started by proving that 1 exists. But it was an incredibly hard class. I was so stressed and I was so worried. And I didn't do that well on the midterm. But by the time I'd gotten to the final, I'd stuck with it and I'd put my everything into it, and I was having a lot of fun. I realized when I was studying for the final at some point, as I was reading this very famous theoretical linear algebra book called Sheldon Axler, is Linear Algebra Done Right, that book I was loving it. And then I took that final, and I probably overstudied, partially because I was worried, but partially because I was just having fun. And I had so much fun with that final, and I did very well on it. So that was nice too. But I think the gratification of this thing that I thought I might not even be able to do, that I don't know if I'd ever be able to do pure math, that I got it. I think that's what makes it so fun. And science is like the furthest extension of that, because not only do I not know if I can do it, I don't know if anyone can do it. And so like there's higher risk, higher reward.
That's what I was just thinking, is like probably that moment of satisfaction, the harder it was, the more satisfying that moment is.
Yeah. So I think that's one of the great things. I think I unfortunately tend to get bored easily, but I've never ever gotten bored studying chemistry or physics or or any science. I mean, I don't get bored with humanities either. You know, this isn't a dig at them, but certainly, like, I think that I could live 1,000 years. I think I wouldn't get bored of studying this stuff. And I love that I meet so many people here who feel the same way. You know, I went to talks with like Reinhard Genzel, who he says, you know, maybe I'll retire if they make me retire. That's great.
Yes.
I love that. And I know, like, you know, I want to do a job that I enjoy so much that I'm only going to retire if they make me, or you know, if there's a very strong reason to. I think that that's what's so fun to me about science and research in general.
Well, I just interviewed a woman who attended the Lindau meeting as a young scientist in 1963.
Wow.
And first of all, she began in astrophysics, but
I did too.
much like Stephen Chu, she's reinvented herself many times. So she went on to study cancer, virology, coronavirus. And I think she's about 80 years old and she's nowhere near retiring. She's delightful and enthusiastic about all of these sciences.
Yeah. I mean, what I've seen the most, having talked to Nobel laureates, is what the Nobel Prize can give you is the opportunity to completely change focus. And I think that's so good intellectually that I was speaking to Michael Levitt, and I think I asked him, what's the most fun thing, or like the thing that's most exciting you right now? And he had a very long answer in which he partially said that he doesn't like to rank things. So I don't want to put words in his mouth. But one of the things he mentioned enjoying a lot was analyzing COVID statistics. And I was like, this is a chemical physicist and a structural biologist, and he's done all these things. And he's out here, his most exciting thing while he's at a chemistry Nobel meeting is COVID statistics. So I think that, you know, and he's actually at a school of public health, and he's done incredible things for that. So I think that, and he was doing it before he won the Nobel too, but that it gives you the opportunity to just totally approach new problems. Stephen Chu is doing, you know, chemistry, hardcore synthesis chemistry.
Far removed from the physics, the laser cooling of atoms, the physics work that he won the Nobel Prize for. He's also done several things in between.
Yeah, and so I think as somebody who also, you know, I can't make up my mind about what I like. That's part of why I'm deferring it by doing both of these. I think that, well, and also because physics and chemistry are not different. Really, all science shares a lot.
And you don't know what you might gain from that interdisciplinary
for sure.
interacting.
So yeah, but I don't remember what I was saying. Well, anyway, yeah. I mean, I think that it's so refreshing to see. That's what it was. It's so refreshing to see that these people are doing such interdisciplinary work, and they're so interested in all these different things, and that, you know, becoming super famous for this, you know, they're not forced to just always do that. And actually, the fame is what allows them, in part, to do whatever they want. And usually, whatever they want is often something entirely different.
In Stephen Chu's talk yesterday, you could get that sense. He admitted that as he moved into these new fields, he was learning. Here's a Nobel, like you said, famous for Nobel Prize winning physicist who also went on to be Secretary of Energy for the United States under President Obama. And then he went into fields that he wasn't a master of, and he didn't know that much chemistry and doesn't know. But he has a lab and he has other people working with him.
And I think he's gotten, I think as a PI in general, I think their job, they get very used to efficiently synthesizing complex understandings of material without a class, you know, by just reading the literature, because that's their whole job. I mean, grad students is part of the job, undergrads is part of the job, but for a PI, everyone's trusting you to make that push, to direct the group. And so I think that that's something that they get used to. And so for him, you know, he did that as a PI in his own field, and then he did that with energy policy in the US, and then he's doing it now in chemistry. And you know, I think that that's what I mean is if you're a scientist, you're really learning how to learn, I think almost always. And so, you know, he's a great example of that, that I think that there's nothing that I couldn't, you know, if he wanted to learn about something, there's nothing I don't think that he couldn't be an expert on. And I really think most people, almost everybody, could be an expert on anything if they wanted to. but I do think it helps a lot when you enjoy it. So that helps a lot too. Is I enjoy biology and humanities, and I think I could become an expert musician or something, and I love playing music, but I think like there's nothing quite like learning about physics and chemistry for me. Except everything else that's related.
Well, the great thing is you're young and you already realize, so many people don't understand that you can change your mind, you can reinvent yourself. You don't, even if you're famous for this thing, you don't have to, that label doesn't have to limit you. And I think that, and you know what, this is, maybe it's a little cliche, but early on when you talked about, and I'd like to, apparently we could talk for a very long time.
Yeah.
And but so I want to talk about the meeting a little. And when you said that, even though it didn't seem likely you're a freshman in college to apply to this meeting, you went ahead and took the shot. And there's this line, it's often attributed to this hockey player, Wayne Gretzky, that you miss 100% of the shots that you don't take.
Yeah.
Maybe it's a little cliche, but that has been very significant in my career in the past decade or so, because I have stepped out of my comfort zone and I've dared to ask someone for a favor or to do a thing, or I tried something I'd never tried before. And I can't tell you, there are some things where I did that where later I was like, oh my God, what if I hadn't asked? Because it worked. So it's like, I think it may be a little cliche, but it's become an important attitude towards me.
Yeah, I mean, there are two quotes that have been constantly on my mind during this meeting. There's also a third one that was really funny by Stephen Chu. I guess I'll say that one first. So he said during his talk something like, the second law of thermodynamics, there's no lobbying group that's strong enough to defeat the second law of thermodynamics. And I say this because a politician has asked me that once. I just think that was so funny. That quote's been on my mind a lot. But there's the quote that you mentioned, and then also, because every time I go up and talk to one of these Nobel laureates, I'm thinking the same thing. I'm thinking, I'm terrified. I don't know enough about their research. What if they say something? What if I say something wrong? They're super nice, but I'm terrified. And then I think, if I don't talk to them, well, then I've definitely done something wrong. Or not wrong in the sense, but I haven't done anything.
So let me point out something. Like early on, you said something about physics or chemistry, and I think you said you're no good in the lab. Aren't you a little young to be deciding you're no good in the lab?
So what I mean is, I don't think that the lab is as fun.
Okay.
I think I could be good in the lab probably if I put a lot of work into it, but I think that my experiences have always been that I don't have great hand-eye coordination. I'm a little clunky. I stumble sometimes, and I think it's a lot nicer when you have an undo button, which you don't always in computational stuff. You got to be careful. But I think I love the lab and I appreciate it. But I mean, yeah, maybe I'll change my mind.
Yeah, and also, there's this idea of like when you try something like an instrument, a musical instrument, or a sport or anything, and you're not good at it, and you're not immediately good at it, so you shy away from it. It's like, well, you're not good at it because you've never done it before. And I don't know if I have an old friend who's a comedian who became pretty famous, Mitch Hedberg, and he had a great joke that summed it up. He said that I taught myself how to play guitar, which was a bad idea because I didn't know how to play.
No, I think about that so often too. I actually think about it in chemistry terms, that if you want to explore a passion, there is an activation energy. So there's a hill you have to get over. You have to sink a certain amount of effort in to even figure out where it's going to take you. And that's scary sometimes. But a lot of what I appreciate about the kind of liberal arts education I got in high school was, as much as I did not enjoy some classes, I almost always, by the end, gained a deep appreciation for the subject, even if I knew it wasn't what I was going to do. And the best example of that is chemistry. My first chemistry class, I hated it. I thought it was so tedious and confusing and all this jargon, which I was yet to realize deeply how much jargon there is in all science. But I really didn't enjoy it. And then I just put enough time in, and I think it was around the time that we started talking about intermolecular forces and like how solids and things are stuck together, which is not by covalent bonds most of the time.
What is it by?
So it's usually, there's a lot of things, but it's traditionally would be like van der Waals forces or hydrogen bonds, which are not actually covalent bonds. So it's they're interactions that happen because of you have a molecule and there's regions of higher or lower electron density around the molecule. And so a lower region is more positive, and that will attract a higher region in another molecule.
Right.
And so you have these broader structures that form from that. That's how the
That's
vast
sort of the
majority.
cohesiveness of water.
Yeah.
Yeah.
So that's.
But
how,
I hope I didn't derail you from the point you were
good.
going to.
Yeah. So actually,
I did.
I'm forgetting a little bit. Wait, let me
But
retrace. So what was I thinking about? It was. We got to that point, and I realized that this is physics, and it's it's the kind of physics that I was missing. The kind where you learn the principles, but then you see exactly how it applies. That I can look at the ground in front of me, and I can think about the physics going on inside the bonds, but I can also think about the fact that those bonds and the intermolecular forces in great bulk lead to what I'm looking at. And so I really think that was the moment that I realized, I mean, there wasn't one moment, but that was one of the moments that I really realized that, like, this chemistry stuff is actually fantastic, that it's exactly the kind of applications of physics that I love. Because, I've thought about a lot of things. I used to want to do astrophysics, and I did a little bit in high school.
And maybe someday you will.
Maybe I will. I mean, this is not at all final.
Right.
In fact, I'd love to. But I felt like those problems, I couldn't see them and I couldn't feel them, and you can't see or feel quantum mechanics, but you can see and feel chemistry, and chemistry, it turns out, is quantum mechanics. And astrophysics, I'm sure that you can often feel things, and I love astrophysics, so that's not at all a dig at that. But I just think that it was so immediately clear to me, not immediately, but chemistry, in that moment, I realized how much I loved it. And I kind of was still convinced I'd be a physicist or even something else at that point. And so I kind of slowly drifted along, and my teacher at one point kind of nudged me and was like, I'm hosting the chemistry Olympiad. You should try out. And I was like, no, I'm not going to do well. And she's like, yeah, but you should just do it. I was also doing science Olympiad at that time, which is more of a team sport. And I was on some chemistry events. And so, again, I felt like I'm just doing it because whatever, I'll learn a little bit. This isn't for me. I'm not a chemist. And then I did it, and somehow I got placed to like the national qualifying level. And then I was around all these serious people, these kids who'd been running experiments in their garages since they were like 7. And their passion really shone through to me. And so anyway, that's a long-winded way of saying what set me on this track was, even though I didn't want to, being forced to invest that activation energy. So I think about that a ton with anything I don't know. That, whether or not I'll be good at something, I really don't know until I put in the activation energy. And I think that's true of everyone.
I'm glad you brought it back around to that, because I love that activation energy analogy. And it reminded me, here's a very simple version. Very often when I listen to an album, the song that I first love best, and there might be a song that I first love best, and there might be other songs that I don't like and I even skip. Very often, eventually, that song that I always skipped ends up being my favorite song on the album. And like over the one that first grabbed me, it's like I don't know. I think there was just something challenging or different. It didn't grab me, but ultimately that became my favorite song on the album. Yeah. Somehow I connect that. Yeah.
Yeah, I agree. I actually have a very similar experience. That more with artists. That I'll hear a song from an artist and go, "Wow, that's weird." Mm-hmm. I don't know how I feel about that. A lot of times it's something that's kind of alternative or whatever, and I'll be like, "This is interesting." but I'm not going to put it on my playlist. And then it'll pop up again, and I'll listen to it, and eventually maybe I'll be like, oh, this is pretty cool, and I'll put it in. I have a playlist that I call like other songs. I kind of just don't know what to categorize, and I'll throw it in there, and then I'll think about it at some point, and I'll be like, man, I kind of want to listen to that song, and eventually it'll wind up in like my favorites playlist. And so I think it's the same thing in part that growing appreciation for things takes time, and it's accelerated when you meet people who appreciate it already. I think meeting passionate people helps immensely in growing your own passion. And I was incredibly lucky that my teachers in high school were so passionate. And it wasn't just chemistry. I mean, I think my government teacher was probably one of the best teachers I've ever had. And that was, it's more important than ever as a scientist and, in the US. So I think about that a lot too. So, I think about that all the time, that I'm always amazed by my own capabilities, and I don't think I'm special in that regard. Like I don't think there's anything about me that's, I need to learn. Like, it takes an activation energy for me, but someone else couldn't do it. I think that it's really just everybody is often always capable of more than they think, and often it's just about deciding how much energy is worth putting in to see, whether it's enjoyable or whether it's worth doing. But I think I do my best, despite often being afraid, to not let that fear influence my actions and to do it anyway and explore. But also I would encourage that, don't let your past experiences or your fear of someone else being better than you or being behind, get in the way. Like I'm a sophomore undergrad. That does not mean that if you're a postdoc, you're too old to apply as a young scientist. Like, absolutely not. In fact, most of the young scientists are older and postdocs, and they are probably getting an immense amount out of this, as I am. In general, I think any sort of those types of comparisons of, you see the kid who is the genius piano player at like age 6, and you go, well, I guess there's no point in learning piano. No, I think there's absolutely a point in learning piano, because do you like piano? Like, it shouldn't matter. I was never good at math. I wasn't too good at chemistry at first. I still don't know if I'm actually that good at physics. But I enjoy them enough that I've chosen to do them. And so, I think that I would love to live in a world where that's the entire driving force is, compare against yourself and who you used to be and what you'd like to be, and what gets you out of bed in the morning, what makes you excited to go do stuff. I think it's different for everyone, and I'll also say that there's a quote that Martin Chalfie said, which is, nobody knows what they're passionate about, so just pick something and be passionate. And it's the same attitude of put in the activation energy, and you might just find out that you love it.
You know what? There's a similar quotation that I just heard. I don't know who it was, a woman in a video that someone sent me about decisions, and like you might decide, and any level decision, and like say you think, should I go to Stanford or MIT, and you decide to go to Stanford, and then let's say you hate it, yeah. But let's say you hate it, and you go, I should have gone to Stanford. But you don't know that, and that could have been worse. Yeah. And what she said is, it's not about making the right decision. It's about making the decision right.
Yes.
So just like Chalfie said, it's like whatever decision you do make, now put yourself into it and make that be the right decision.
Yeah, absolutely. It doesn't mean that you have to. I sometimes have issue when people say, give your 100% to everything, because we're limited. We're mortal. I think that there are some things you have to prioritize, but I think that certainly, if you're going to do something, make a conscious decision about how much you're going to do it in a way that you feel fully invested in that decision. Like I may not be I'm doing multiple research projects, and I may be doing one more often than another in terms of time commitment. Because I'm a theorist, I can, I could run inside right now and start working on my computer, so I don't have to be in the lab. But I think that it's a conscious decision how much time I'm putting into each thing. And so it doesn't feel like I'm, oh, I should have been doing more with this. Okay, so then, if I feel I'm not, then next time I'll change my mind. I think just being in, there's a word for this, mindful. I hear a lot about this from the psychology side. The importance of mindfulness doesn't mean the importance of blocking everything else out and putting everything into this one thing and dropping out of college and doing this right now and doing this startup and that's all you do. Some people do that. That's cool. But I think what it means is be conscious of what you're doing. Be invested in what you're doing. Don't do something unless your heart's in it. And if your heart is really, really in it, then maybe consider spending more time on it. But time is unfortunately the most important resource on the planet and is very limited. So.
And I'm taking a lot of yours. Would you believe most of the interviews I've done this week are 10 to 12 minutes? I suspect we've gone a little over that. And my only concern at this point in relation to one of the Nobel laureates here, two of the laureates here, Stanley Whittingham, and I'm sorry, I don't remember the other, is the founding father of lithium-ion batteries, is we may actually be running out of battery power. But It's been really nice chatting with you. And because I can't stop either. And one more addendum is like Kurt Vonnegut would encourage you to do whatever it is, art or whatever thing, but it's irrelevant if you're good at it. Just do it, and if you enjoy it, and do it just for the sake of doing it and the enjoyment of doing it. And it doesn't matter if you're good at it.
And it doesn't, I would add to, because this is something I struggled with a lot, it doesn't have to be the thing that you're best at. It doesn't like I want to do chemistry and physics. I don't know what thing within that broad field I'm gonna do or be the best at, and I don't know if what I'm doing is the greatest, 100% most meaningful use of my effort as a person. But I think, like I said, it's what I'm doing right now, and I'm gonna do it. I'm passionate about it, and don't let that ruin your passion. If someone says, like I've had discussions with people where they're like, well, yeah, but your work is not, it's not very applicable. It's not groundbreaking. Well, first of all, I'm an undergrad, so I don't expect that. But I think that you can keep that in mind, and it's helpful for getting grant funding. But I think whatever you're doing, find a way to enjoy it for what it is, and not for what it's not. And you never know, because so many of these people I've met, the thing that got them their Nobel Prizes was completely unexpected, or it was something that they had already wanted to do for a long time. So I think that the third quote, this would be a great way to round out, that I think about a ton, is there's this quote by Jim Carrey in a speech he gave somewhere, and he's talking about his father, and he says something along the lines of, you can fail at what you don't love, so you might as well try at what you do. And I think about that a lot. Like, I think it'd be more fun to not, have a Nobel Prize and be super influential, but just enjoy my life doing the things that I enjoy and that make me happy and passionate, than to direct my whole career strategically toward, something that I think is going to be a breakthrough, but I don't enjoy as much, and then never have it play out. Obviously, it'd be great to have the Venn diagram be on both, but it's hard to find those things. That's the golden question that I'm sure people would love to answer. So.
Well, that's fantastic, and I think you're already along a great path at an early stage in your life, and it can be a little humbling, but it's also encouraging to be outshone in eloquence and insight by someone who recently finished their freshman year of college. But yeah, I'm glad you're enjoying this. I'm sorry that I've taken you away from so much of it.
No, I had fun.
But this has been a great conversation.
Yeah.
And enjoy the rest of this conference. You seem to be doing a good job of it and getting a lot out of it.
Yeah, I'm having so much fun.
I mean, I would almost, I have nothing more, I would say, what would you tell to young scientists? But I think you've said it all. This has been a lot of fun. And Ladies and gentlemen, maybe the future is bright.
I don't know.
So yeah, thanks. Let's wrap this up. And I'm excited to see how long we've talked and also how much battery power I have left.
Yeah, sorry about that.
No. Hey, I could have stopped us at any time. I didn't want to. So this is, and I mean this as a positive thing. It's the longest interview I've done here this week, and I mean that as a compliment. It was a great conversation.
Yeah.
So
Thank you very much.
I hope you enjoyed it too.
And you are very good at figuring out the right questions to ask.
Cool.
You're a great
Thank you very
interviewer.
much.
Thank you.
Your good answers made it easy too. So we're going to just keep complimenting each other unless I just hit the stop button. So we've been live from the 74th Lindau Nobel Laureate Meeting. I wish you could see how amazing the clouds
I've
look
been
right
looking the
now in
whole
front of
time.
us, which
it's so
I
gorgeous.
mean, yeah, it's beautiful. I mean, I don't know why you can't, except that my head is in the way and I'm not really doing it justice. But we're on a beautiful medieval island on a beautiful lake, and having a lot of beautiful experiences. Thank you, Simon.
Yeah.
Simon Nirenberg. Let's see if we hear his name again sometime. I wouldn't be surprised. I'm gonna finally let myself say goodbye.
Thank you.